you doing?
I'm doing good.
Can you go ahead and introduce yourself and the projects that you have done?
Actually, I started my career in 2020 with the Mirafra Technologies. Before that, I did some training from RV Skills from Bangalore. After that, I joined Mirafra, but just because of lack of projects for the freshers, after that I joined Sign of Semiconductor. But in Mirafra, I did some projects as well. Like it was internal projects. You can say it's for my improvement only. I did only from my side only in a 14 nanometer. The projects was like a flash ADC I did, level shifter
Okay.
I did, LDO I did. Uh, these are the projects I did in the 14 nanometer. After that, I went to the Sign of Semiconductor. There I worked on PLL, sub-models of the PLL, sub-blocks of the ESD in 16 nanometer. Apart from that, we did some blocks on drivers like heavy range, hybrid regulators also we did. Regulators I did average regulator, hybrid regulators, and yeah, those the regulators I did in the 16 nanometers. Again, we did high performance standard cells and high density standard cells also we did.
Okay. So,
And
what
in
were?
the hmm?
Yeah, you were saying something.
Yeah, in the verification part, I did DRC, LVS, and in the EST, we did some density checks, which is available in the DRC only.
Okay. Okay. So, we'll be starting with the basics.
Okay.
So, what are the kind of matching that you have come across while doing the blocks? Are you aware of the type of the matching?
Oh yeah, matchings. We did two types of matchings. We have differential for differential pairs. We generally do like a common centroid, and current mirrors we are doing the interdigitization just to avoid the process variations.
Yeah. Okay. So, I'll give you one question. If A is equal to 1 and B is equal to 1 and C is equal to 5 and D is equal to 5, how would you match it using common centroid? Do you have pen and
Just
paper with you?
just wait. Yeah, can you repeat?
So your A is equal to 1, B is equal to 1, C is equal to 5 and D is equal to 5. How would you match it using common centroid?
Okay, just wait. It's a common centroid.
Yeah.
Okay.
Yeah. Just
Yeah, it's
show
a
the.
okay. I can okay, I will write in big letters. It won't be visible for you.
Okay. Yeah, that seems okay.
Okay.
And you said you have worked on EDC, right? What were the challenges you faced over there?
Metallization actually. The current requirement for ESD is very high, like we did for the 7 ampere. If the current is like in a micro or a milliampere, it is easy to do the power mesh. But like if I talk about, suppose there are a lot of diodes we have in a ESD, like HIA diode we have, a drain ballasted we have, gated diode we have. So the those devices we have to design for the 7 ampere. But if I say whenever we generate any device, whenever we instantiate, so we know the size of a device, it is not capable to carry like a 7 ampere. So we have to take the so many multipliers we have to calculate. So for 7 ampere current, I have to take like around 700, 800 multipliers. Then only I can do the routings. Means alone single device can't carry the 7 amperes. So we depends on the width of the metal. We have to calculate a single device how much current can carry. So based on that, metal stack I have to do. If one device in a one row is carrying this much of current, so what should be the metal stack? So how
Okay.
many rows are there? When I will connect all those rows, so what should be the metal width? This was the first project for me to calculate this much of a current. So to do the metallization or say the current, as per the current requirement to trace the metallization, it was difficult for me.
Okay. So, are you aware of the ways to mitigate the ESD?
Means,
Um, as in, how do you overcome the ESD? The ways to overcome ESD.
okay, initially I was not aware means suppose one diode is there, a gated diode is there. I instantiate the diode's size of that, it was very less. And the metallization which I did, it was very something different. It was not getting match. So after that, I came to know like one device, like we have a source and drain in the devices. Suppose it's a diode, so two terminals we have P and N. So P diode, what is the metal width? We have a DRM. In DRM, we have a formula for the current calculation. So this much of width, if you have, then how much current can carry? So I checked the capacity of the each devices, and then I thought if I take the two devices, then the current it can carry a little bit more. So after that, I took little bit more devices and tried to negotiate those things. Then I took the lot of multipliers, and then I came to know like we need this much of a multipliers, then only we can carry this much of current.
Okay. Okay. Then, have you worked on shielding?
Yeah, shielding I work.
Can you tell me what the shielding is and types of shielding?
First thing we should know like why we are using the shielding. Like to avoid the crosstalk. Crosstalk means suppose we have a two metals. Okay, and inside the two metals, any metal materials will be there. Like air will be there. Any materials can be there, or means SiO2 can be there. So it act as a insulator or say the dielectric. Then it act as a capacitor. So unwantedly, suppose we have a two nets. One of the net is the victim net, and other net is the aggressive. So aggressive net have some unwanted charges, we can say the noise. So when it acts as a capacitor, so victim net will get some unwanted charges from the aggressive net, so it will get collapse means the victim net will get some other noises as well. So to avoid those things, we have to shield means we have to protect that particular net, that victim net, which is important for us. Like a data nets you can say, or the clock signals you can say, these are the important nets. We have to protect this net from other nets who is carrying the noise or unwanted charges. So we have a two types of shielding, like a sidewall shielding and a coaxial. Sidewall shielding means from two sides we have to use the metal, and that we have to connect with the powers. And coaxial means from all the sides we have to connect the metals, and that one we have to connect to the powers. It can be the ground or power, VDD, but mostly we are connecting with the ground because ground is the more stable than power, VDD.
Okay. And have you worked on antenna effect?
I didn't work on antenna effect, but the concept I know.
Okay. So, do you are you aware of ways to overcome antenna effect?
Yeah, the solutions I know.
Okay. Can you briefly tell me
Yeah.
about it?
First, we should know like what is the antenna effect. Antenna effect means wherever the dielectric, that Si to select silicon dielectric is available, like in the gate we have Si2. So there this charge is getting affected. Whenever the lengthy metal is connected to the gate, so a lot of charges are there in the lengthy metal. So we have to break anyhow that lengthy metal. Some other preventions are there. So as we apply some voltage, or some say when we apply in the voltage, or during the plasma etching, actually in the manufacturing, in the fabrication process, some plasma etching is going on. So what will happen? Charges will get induced in the metal. If metal is lengthy, then definitely there will be the more charges. So that will hit to the gate terminal, and gate terminal will get damaged because of the lot of charges. So we have to prevent our gate terminal, otherwise our device will never get turned on. So solutions are like we can use the higher metals through the jumpers. The higher jumpers will help to reduce the antenna in this way. Like in the fabrication process, first metal one will get fabricated. After that, metal two will get fabricated. After that, metal three. While fabrication of a metal one, charges will be only within the metal one. It will not jump on the metal two. because fabrication is going on for the metal one. So the length for the metal one is already less, so the charges will be less. After that, metal 2 will get fabricated. Then again for metal 2, the charges will be less. So this is the first method, and second method is we can use the antenna diode. The diode is the normal diode, but we are using to reduce the antenna. That's why it is the antenna diode. Diode we have to connect near to the gate terminal, and reverse bias diode we are using for the antenna. Reverse bias diode, it is because forward bias diode works for the low voltage, like to turn on the device for the MOSFET or say PMOS or NMOS, we require a very less operating voltage, means 0 to 5 volt we can say. Forward bias diode also works for the low voltage, like 0 to 5 volt. When it comes to the real operation, if we apply 0 to 5 volts, forward diode, forward bias diode will get turned on, and all the charges will pass to the ground, or say all the charges will pass through the diode. Your original device will never get turned on. That's why the forward bias diode is not in use, and reverse bias diode used for the higher voltage. In the fabrication, while doing the plasma etching, the charges are very high and the voltage is very high. So whenever the charges will come towards the reverse bias, it will get turned on, and all the charges will pass to the ground. Your original device will get protected. None of the charges will go towards the original device. And even when you come to the real operation, 0 to 5 volt we are giving to the real operation. So if you give 0 to 5 volt to the device, your reverse bias diode will never get turned on. That's why the reverse bias diode is used in antenna effect.
You said that we are going for higher metal. What was the first solution? You said we were going for higher metals, right?
Yeah.
So how
Higher metals through the jumper.
Yeah, so still the charges can get accumulated, right? There is one process which removes the charges. What is
Yeah.
it? How is like even if we are going through like for higher metals, still charges are there. Then why is it not damaging our gate?
Actually, charges will be there, but the length of the metal will be the less. Instead of using the one continuous metal, we are using the pieces of the metals. And the metal one means as we go on the higher metal based on the metal stack, their capacity to carry that much of charge is little bit good. Like their resistance and also current will flow very, means they will oppose to flow the charges.
Okay.
And if still the charges are there, then we have to use the antenna diode as well.
Okay. Are you aware of latch-up?
Yeah.
Can you briefly tell me about it?
Okay. Latch up is a condition where your power supply, VDD and VSS, ground, both get shorts. It creates a low impedance path between power and ground. Actually, due to some spikes or some leakage, your when some unbounce comes, like your power, some fluctuations in powers and grounds or inputs and outputs, just because of that, some parasitic BJTs get triggered on. Parasitic BJTs will get formed in your device inverter. So that parasitic BJT will help to flow the charge from power supply to ground continuously and vice versa. So they will create a path in a way, like even if you give the small voltage, so your current will flow continuously from power to ground and ground to power.
You said the parasitic will help
Parasitic
the.
BJTs will get triggered on.
Okay. Okay. Uh, what are the ways to mitigate latch-up?
Like first thing, the guarding we can use. The guarding will break your ODs, or some say it will absorb all the minority carriers. Like for NMOS, we are using the P type of a guarding, P sub guarding, or a PMOS NWell type of a guarding. So whenever you are using the guarding, whatever the devices are there inside the guarding, your minority carriers will not cross to the guarding. Like minority carriers from PMOS to NMOS will not flow. So guarding is the first solution. The second is like we can increase the contacts. Contacts means contacts will increase the resistance. PWell and NWell contacts we can add more. They will help to increase the resistance. If your resistance will increase, so it will help to reduce the current. And deep anvil also we can use. Deep anvil is mostly absorb the minority carriers also. Like suppose if your any device is, suppose I have a 5 NMOSes, out of them one is connected, out of them 4 is connected to the ground. There are tap cells, their body is connected to the ground, and one of the fifth one, like suppose fifth one NMOS is not connected to the ground. So that fifth one we have to differentiate from the 4. Otherwise, some extra charges will occur and it will get short. So that fifth one, which is not connected to the ground, its body, that we have to differentiate. That we have to keep in a deep anvil so that latch up we can occur. And the STI also we can use. STI means shallow trains isolation. In between the two ODs, we have to fill the space with the some dielectric material. So it will help to not flow magnetic carriers from one location to other location, or say one device to other device. Again,
Okay.
insulators also we can add on PMOS and NMOS. So that insulator will not allow to flow the minority carriers from P or from source or drain to the P substrate.
Okay. Um, where does latch up generally occur? The areas which are prone to latch up. How do you decide? Like, do you have to put the guard rings or give other ways to s- solve the latch up?
Latch up guarding, if I talk about the guarding is nothing but your body or say the tap cell. So in an analog part, the guarding is the only one we have as a body. Okay, and like wherever the three terminals are there, if I talk about the inverters, how BJTs get triggered on? The for the BJTs have a 3 terminals N, P, N. So wherever these layers are there, their BJTs can trigger on parasitic and their latch up can occur.
Okay. And are you aware of EMNIR?
Yeah.
Can you
Electromigration
give?
occurs because of a high current density. It is based on the momentum of an electron. When electron flows from one direction to the other direction, one location to other location, so your current density will be the high, and because of the high current density, either your charges will be more, or it will be like your metals will get either short or open,
Yeah.
and just like you can say like void and ghost kind of structure it will create, bump and unbump, because of high current density and more powers. So instead of a 2 milliampere current, suppose it can flow more or less. As a current density is just because of the high current density, your temperature will be also increased, and if temperature get increases, so current will also increase, and your resistance will get decreased, and this process will be continuous, and your metal will get damaged permanently. And
Okay.
IR is related to the voltage drop. In a lengthy metal, we don't know how many resistors are there in metals. Suppose 5 resistors are there, and I'm applying the 5 volts. So after one resistor, there can be the voltage drop like a 4.9 or 4.7. After again certain location, means after second register, voltage will be dropped. Then like 4.5, 4.6, and I want like proper 5 volt to get the turn on device. So because of voltage drop, my original device will not get turn on. That is the voltage drop.
Okay. So how do you avoid IR drop?
Higher drop, we have to widen the metal, or higher metal we have to use. Metal stacks also we can use. Contacts we have to add more contacts.
Okay. And
Initially, before the routing, we have to decide what should be the metal width based on your current and voltage requirement.
yes. And ways to avoid electromigration.
Just wait, your voice is not. Yeah, can you repeat the question?
Ways to avoid electromigration.
Both are EM and I are both are like a twins brother. So EM is also the same way. For EM, parallel path also we can use for electromigration, and EM
Yes.
also we can use the higher metals also.
Okay.
For a EM, as a layout engineer, we are not handling, but we can play with the operating voltages and frequency as well.
And okay. So are you aware of layout dependent effects? Any like,
A layout dependent effects means like what?
well proximity effect?
Yeah, well, proximity effect is related to the ion implantation. Like suppose I have a five PMOS in the N well. Okay, I have a five PMOSes in the one single N well, and while doing the ion implantation, what will happen? Like implantation we are doing from the top side. Okay, so in between device like second to fourth device will get the uniform ion particles, but the first and fifth means the first and last, because of the n well is near to them, so ion particles will hit to the n well and will get deposit on the corners devices like the first and last one. So the ion particles for the first and last will be the more as compared to the in between devices. So the VT for the first and last devices will be something different, and in between devices it can be the less or different. So this is the well proximity effect that it will affect on your threshold voltage.
Okay, so which devices do get affected? The devices which are close to the well
And
boundary,
well,
or
yes,
which one? Just
and well.
the devices which are on the extreme, those, or the devices which are at the center, can they be affected as well?
The devices which are close to the well boundaries, those will get more effective.
Okay.
So as a solution, the spacing between the N-well to the main device, that closest one, the last devices we can increase, or the dummies we can place and the corners.
Yeah. So well proximity effect, does it only occur for PMOS or does it occur for
No,
NMOSs?
it is for both.
Okay. Okay, that's all from my end. Rachit, one second. We'll update you for any further rounds.
Yeah, sure. No.
Okay. Just one.
Yeah, thank you.
Thank you.
Yeah, thank you. Thanks for your valuable time. In night, I disturb you. Sorry.
What's up?